So in the last two sessions, we discussed three Sylow theorems. They are actually giving some information about the order of the subgroups. So what we'll do today, we'll do some examples and some problems using these theorems. So let us state those three theorems first. The first theorem is first Sylow's theorem says that if the order of G is finite and is equal to p to the power of n times m, where p is a prime and m does not divide p, then there exist subgroups of G of order p to the power of I for all 1 less than or equal to I less than or equal to n. And the second part of this theorem is p to the power of I is a normal subgroup of p to the power of I plus 1 for all 1 less than or equal to I less than n. So this is the first theorem, and the second theorem says that if p1 and p2 are Sylow's p subgroups of a finite group G, then p1 and p2 are conjugates. This is the second theorem. And the third theorem says that it gives you the number of Sylow's p, gives you an idea of the number of Sylow's p subgroups. So if G is a finite group and p divides the order of G, where p is a prime, then the number of Sylow's p groups is 1 mod p and divides the order of G. So we are going to use these theorems to do some problems. The first problem we are going to try is to find out all Sylow's two subgroups of S4. S4 is actually is a symmetric group on 4 elements. So S4 contains 4 factorial elements, and that is 24 elements. 24. So we are trying to find out the number of 2 subgroups, and 24 is equal to 2 cube times 3. So the order of Sylow's 2 subgroups is 2 cube, that is 8. And number of Sylow's two subgroups of S4 is 1 mod 2. So it could be is either either 1 or 3 or 5, 7, etc. Okay, and the number of Sylow's 2 subgroups should divide 24. So it could be, so the number of 2 subgroups, Sylow's 2 subgroups is either 1 or 3. So what we'll do is we'll find out 1 and we'll see if there is any other subgroup that is conjugate to that. If there are, then it should be 3. We know there is a subgroup. So any subgroup of order 8 is a Sylow subgroup. But we know a subgroup of S4 that is of order 8. It is a dihedral subgroup. So D4 is a subgroup of S4 of order 8. This is actually, if you remember, is 1, 2, 3, 4. If you order it like this, then these are the symmetric changes of symmetric permutation of these 2, 3, these 4 vertices. So it is actually rotation, 4 rotations, and one of them is the identity. Then the image, horizontal and vertical images, and diagonal images. And that is D4. So we can write the elements like this. So if the vertices of a square are named as 1, 2, 3, 4, D4 contains 1, 2, 3, 4, 1, 2, 3, 4. This is our identity. Then we'll have 1, 2, 3, 4, 2, 3, 4, 1. Then we'll have 1, 2, 3, 4, 3, 4, 1, 2, 1, 2, 3, 4, 4, 1, 2, 3. These are the rotations: sigma 0, sigma 1, sigma 2, and sigma 3. Then we'll have horizontal image. So 1, 2, 3, 4. This we'll call it as, okay, D4. Let's call it as H. Okay. Okay. Now this will be vertical. So this will be 2, 1, 4, 3. And we'll have 2, 3, 4. And this will be horizontal. So this will be 4, 1, 3, 2. then you'll have diagonals. Now diagonals 1, 2, 3, 4. Uh, 1 and 3 are fixed, 2 and 3 are, 4 and 2 are changed. Next one will be 1, 2, 3, 4. This will be 1, 2. So these are the 8 elements of D4. But there are some more D4s in here. That we get it by just reordering the vertices. I'm not going to write the whole thing. Reordering the vertices of the square as one reordering will be 1, 2, 4, 3. Alright, sorry, not 1, 2, 4, 3. It will be 1, 3, 4, 2 and 1, 3, 2, 4. Then you recreate D4 with the vertices 1, 3, 4, 2. That means in here you replace 2 with 3 and 3 with 4 and 4 with 2. And you get another sequence of permutations, and that will form another subgroup, and we'll call that one as K. I'm not going to write the whole thing. It's just replacing the vertices. Okay, and like that, if you replace the vertices as 1, 3, 2, 4, you get another. So K is formed using K, the subgroup K. The subgroup K is formed by using 1, 3, 4, 2 and L is formed using 1, 3, 2, 4. Why we are doing this? We want to find out whether these subgroups are conjugate of this. Definitely this is a conjugate. Definitely H is a Sylow's 2 subgroups because the order is 8. Order of this one is also 8, but it could be exactly like this. So when we expand this one, you will see that K and L are different and they are different from H. If you take any other combination also, you get the dihedral group like this, but they will be one of the H or K or L. Now we need to find out this. These are conjugate. So verify. I'm not going to do that. Verify K is equal to 2, 3 H 2, 3. See, 2, 3 and 2, 3 are, this is our G and this is our G inverse. The inverse of 2, 3 is itself. This 2, 3 means it's a permutation which moves 2 to 3 and 3 to 2 and keeping 1 and 4 as it is. So this is a permutation in S4. So you can verify If you compute this one, take each element of this one, you'll find that K is equal to 2, 3, H 2, 3. So K is a conjugate of H, and L is equal to 3, 4, H 3, 4. So K and L are conjugates, and that's what the second Sylow's theorem states. If two Sylow's P subgroups are, if P1 and P2 are two Sylow's P subgroups, they are conjugates, and that's what this one is. So this is a good example of showing the second Sylow's theorem. Our next problem is this. Let G be a finite group and P and Q are primes and divide the order of G. If G has only one Sylow's P subgroup, then G is not simple. G is not simple means a group G is simple if it does not have any proper normal subgroup. Proper non-trivial normal subgroups. Then G is simple. So let H be the Sylow's P subgroup of G. There is only one. There is only one Sylow's P subgroup of G. Since Q divides order of G, and I'm assuming that P and Q are distinct primes, and P and Q are distinct primes, the order of G is different from the order of H, implies H is not equal to G. So, see, H is a Sylow's P subgroup. So, G H G inverse is a conjugate of H, and hence GH G inverse is also a Sylow's P subgroup for all G in G. But there is only one Sylow's P subgroup that is given. But GH G inverse is equal to H for all G in G because there is only one Sylow's P subgroup of G. what does this mean? This implies H is normal in G. And H is a proper subgroup of G. And that implies G is not simple. Our next problem is this. Every group of order 45 has a normal subgroup of order 9. So let G be a group of order 45. That is equal to 45, and that is equal to 3 square times 5. So the order of Sylow's 3 group is 3 square equal to 9. The number of Sylow's 3 subgroup should be either 1 or 4 or 7 dash dash, and should divide 45. So if you take this series until you reach 45, you will find that there's only one divides 45. None of the others will divide 45. So the only possible number of Sylow's P subgroup of a group of order 45 is 1. So that, what does that mean? That means so let HB, we want to show that the subgroup of order 9 is normal in G. Okay? Because we found that there is a subgroup of order 9. We want to show that it is normal. Let H be the subgroup of order 9 in G. We know that there is a subgroup like this. Okay? That implies G inverse is also a subgroup of order 9 and is a 3 subgroup. Sylow's 3 subgroup. So Sylow's 3 subgroup of G. This is actually 3 subgroup instead of P. But there is only one such group. Since there is only one subgroup of order 9 in G, G inverse must be equal to H, and that implies H is normal in G. So there is a subgroup of order 9, a normal subgroup of order 9 in a group of order 45. Now our next problem is this. Let G be a finite group and P is a prime that divides order of G. Let P be a Sylow P subgroup of G and H be a P subgroup of G. Then there exists a G in G such that G H G inverse is a subgroup of. This is a very simple problem. Let us understand what it says. P is a Sylow P subgroup and H is just a P subgroup. The difference is P is maximal, meaning if the order of G is equal to P to the power of n times m, the order of P is going to be P to the power of n. And the order of H could be anything less than this, P to the power of I less than or equal to. So this will be 1 less than or equal to I less than or equal to n. So H is smaller than P, size wise. Doesn't need to be a subgroup. So what the problem states is that H doesn't need to be a subgroup of any Sylow P subgroup, but we can find an element G such that we can make a conjugate of H to be a subgroup of P. Right? So the proof goes like this. From the first Sylow theorem, there exists a Sylow P subgroup, let's say K, that contains H, because the order of H would be Pi and order of K would be P to the power of n. This is the maximum, and we know that from I, for each I, we have a sequence of normal subgroups. So we can always find a Sylow P subgroup that contains this, but that does not necessarily have to be P. So K and P are Sylow P subgroups. So here what this means that H is a subgroup of K. Right? So P and K and P are Sylow P subgroup implies K and P are conjugates. And that implies that implies P is equal to G K G inverse for some G in G. So K is a subgroup of H is a subgroup of K implies GH G inverse is a subgroup of G K G inverse. You are adding G and G inverse on both sides, and that implies GH G inverse, this is nothing but our P, and that's what we want to show. So our next problem is this. Let G be a finite group of order p to the power of r times m, where p is a prime number, r is greater than 0, an integer, a positive integer, and m is strictly less than G cannot be a simple group. Meaning, we are going to find a proper non-trivial normal subgroup of G, and that is going to be a Sylow P subgroup of G. So we are going to show that there exists only one Sylow P subgroup for G. If there is only one, then that is normal. Okay, so the number of Sylow's P subgroups of G is congruent to 1 mod P. And because m is less than P, this number can be only 1, because the next number will be 1. There is no other number that can divide G. So you can say here, and the number of Sylow's P subgroups should divide G. It should divide G and it should be congruent to 1 mod P. And since m is strictly less than P, the only possible number of P, Sylow's P subgroup is 1. Implies G has only one Sylow's P subgroup, and that implies every conjugate subgroups of the Sylow's P subgroup are same as itself. implies G inverse equal to P for all G in G, where P is a Sylow's subgroup, Sylow's P subgroup, and that implies P is normal in G. And since when you assume that M is greater than 1, since 1 less than or equal to less than M less than P, P is a proper normal subgroup of G, and that implies G is not simple. We'll do another problem. Let G be a finite group and P be a normal P subgroup of G. Then P is contained in every Sylow's P subgroup. See, let us understand what the problem is. See, for any group, if P divides the order of G, then we have several P1, P2 dash dash PR, Sylow's P groups. Okay, these are all order is same. This is n. This is also p to the power of n dash dash. This is also p to the power of n, and these are conjugates each other. If you take any two, one of them is the conjugate of the other. So for this P, there is a sequence of P subgroups. Let us say P1 n minus 1, P1 n minus 2 dash dash dash. So this is actually, there is a sequence of P subgroups here, and there is a sequence of P subgroups here, and there is a sequence of P subgroups. These are all different. But what this problem says that if one of this, let us say P I n minus k, if this is a normal subgroup of G, then from here onwards, so then this is contained in every Sylow's P subgroup, meaning there is only one. We can find a sequence of P groups starting from here onwards to PR. So it's a very interesting problem, but very easy to prove. Okay, so proof. So P is a normal P subgroup of G implies there exists a Sylow's P subgroup K containing P. That means P is less than or equal to K. This is one of these PIs, and this P is this. Now, every Sylow's P subgroup is conjugate to K, and that implies, let us say this is every P subgroup, let us call it as L. So that means L is equal to G K G inverse for some G in. So from here, P is subgroup of K implies GP inverse, GP G inverse is a subgroup of GK G inverse. But this is nothing but any Sylow's P subgroup is equal to L. So that implies GP G inverse is a subgroup of any Syllow's P subgroup. GP G inverse is a subgroup of any Syllow's P subgroup. But GP G inverse is nothing but P because P is normal. So this implies P is a subgroup of L, which is any Syllow's P subgroup, and that's what we want to show.